Okay, thank you. Okay, so I'm from the Cambridge Cryptographic Data Centre based in Cambridge. When I wrote this, or proposed this talk, it was, we maintained a database which is 52 years old. Problem with birthdays is they happen every year, so it's now 53 years old. Okay, so just to explain where I come from, we're a non-profit organisation, a spin-off from the chemistry department in Cambridge, essentially. We do all these cool things, but the main thing, or the thing we're known for, is maintaining a database called the Cambridge Structural Database, which is the topic of this talk. The organisation is a mixture of data creators, so these are expert chemists and crystallographers who understand chemistry, software developers, such as myself, don't understand chemistry so much necessarily, and then application scientists who tend to use the chemistry for interesting problems. Okay, so the Cambridge Structural Database is a repository of crystal structures, so every single published three-dimensional structure of molecules of a certain type, so organic or metal-organic chemicals are stored, put into this database. Feedback will stand over there. So stand here. And as you can see from the growth of the database since the 1970s, almost an exponential growth. All the structures in the database are freely available if you follow that link. So this talk is based on the history of that database. Starting in 1965. Before 1965, nothing interesting happened. I try to see what interesting things in 1965 happened. Not much, really, except the CSD was born. Okay, so at the time, there was a perception that the results from individual experiments, so in this particular case, crystallography experiments, so that's the solution of a three-dimensional structure of a molecule, the aggregation of the results is a lot more valuable than the individual experimental results. So in response to that, the CSD was established to collect all the published data into one place, it's accessible and can be used as a whole. So the lady there was the first director of the institute. The middle guy is a very famous crystallographer called Jack Dunnett's little quote that it basically had the belief that the set of knowledge was more valuable than the individual pieces of information. So around 1965 and then the years after, we weren't the only structural database that was set up. Each of these has a different set of chemistries it's interested in. So in our case, the Cambridge Structural Database, it's what we call organic or organometallic compounds, and they're the type of compounds that are interested in, if you're in the pharmaceutical industry, say they look like drug molecules, or in the agrochemical industry, they look like pesticides. Small molecules. Protein data bank stores huge molecules, proteins. They tend to be 100 times bigger than the molecules we deal with. The inorganic structured database, they're more dealing with things more like table salt and diamond, so generally sort of ionic, crystalline compounds. And then nucleic acid database, nucleic acids, which form DNA and RNA and similar molecules. And there are other databases, but I think they're the four well-known ones. So why do we care? So just jumping forward to 2018, just so I explain some background of what we can use this information for these days. So if you understand the structure of a molecule and therefore understand the interactions it might make, its conformational preferences, you can start to understand kind of its physical properties when it's crystallized, and you can look at questions like solubility and whether something is going to form a crystal. So an example where this might be useful is if you've designed a wonderful new life-saving medicine and you want to make lots of tablets of it, you have to produce plenty of this stuff, and so you have some industrial plant which carries out the chemical synthesis, and stuff that drops out at the end of that you put into tablets. But if in the middle of your industrial process the compound has a tendency to crystallise, you're going to be hitting problems. So if you understand the physical properties of that crystal in advance, so you can predict these, and you can perhaps choose a slightly different molecule, so it has different properties, or choose a different process, or choose a different synthetic route. Another use is actually in designing the molecule. So a lot of drugs work on the basis that they bind to a particular site in a large protein molecule, and they bind based on where their interactions, chemical interactions, pointing. So if you understand what leads to different conformations and therefore different interactions, you can produce better drugs, or you can come up with new compounds, or refine the compounds you have so they bind in better ways, and you can characterise what you see and improve the chemistries. Okay, so back to history. So 1965. I wasn't around. It was quite a different time. Certainly from a technical perspective, things were very different. The PDP-10 computer was kind of the first, what we'd understand as a computer that was widely adopted in research environments in labs. And that's because it was much cheaper than most of its competitors at the time. So this computer would have cost $18,000, which in today's money is about £100,000. The memory in this cost 50 cents per byte. So if you wanted 32 kilobytes added to your machine, that would double the price of your computer. So cost was a problem, storage capacity was a problem, data standards didn't exist in 1965, and we were trying to maintain or create a database. So as technologies evolved, the database has obviously evolved as well. So the first problem, database. You need to put the data in the database. This is very early days of OCR, for example. This device here, so the CCDC used things called tectonic pucks. So this isn't a tectonic pucks, this is a different competitor, because I didn't find the right picture, but the idea is you draw by hand a chemical structure, and you put it on here, and this little device, pointer device, you put over the atoms, the interesting points, and you go click. And so one of these ladies would have entered all the coordinates by hand, and then for the chemical diagram they'd have drawn it on a piece of paper, put it on there, and click, 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 and enter that into the database. So one of my colleagues is here in the conference, she's not in the room here now, but her first job at CCDC was to replace this system with the entire software system. So on your computer you enter the chemical diagram essentially. In 1991 there was a revolution in how the data was communicated and accessible or shared. So the CIF, chemical interchange format file, was developed. It's a bit blurry on this screen, but there's the front page of the scientific publication, so the International Union of Crystallographers and CCDC and some other notable people in the community got together and they developed a file format for crystal structures. And that was introduced in 91, 92, and this graph shows the fraction of entries going into the database that were manually entered versus those digitally deposited. And very quickly there's a huge and dramatic change in that. So nowadays, more or less 100% of structures in the database come from electronic sources. Generally feeds directly from the publisher or the crystallographer, the scientist, entering the data from their own software in their own lab at the time they're doing an experiment. So distributing the data once you have it in there, that's obviously changed as time's gone on. So we used to publish books. They're like big telephone directories. But instead of names to numbers, they were chemical structures to citations. So the link to the scientific paper where that structure was described. Also went through tapes and CDs. I do have in my bag actually a DVD version from 2012, I was going to wave it around. It's actually as recently as 2014 where we switched to download only. At that point, 99.7% of our users we deemed to have a good quality internet connection. Unfortunately, that still leaves 0.3% of our users who didn't. And so some interesting kind of support activities had to take place to get the data to them. So we had one user in Cuba. That user had dial-up standard internet, couldn't download multiple gigabytes, which would have been required, and the postal service wasn't suitable for sending a hard drive. So I had to meet up with him at a conference in the United States. So one of our application scientists went to a conference with a USB hard drive and handed it to him in person at a scientific conference, which they then took back to Cuba. Yeah, those books, back of the envelope calculation during the week, just under 3 meters long the bookshelf would have to be if we still published books. Okay, so to actually get the data out, it's changed over time, so it started with books. The text searching was fine, the substructure searching not so much, so if you had a particular chemical structure you were interested in, you actually had to physically look through lots and lots of pictures, kind of finding someone's name based on their telephone number in the telephone book. So that's a program called Quest, written in Fortran, Fortran 77 initially, which gave a graphical means to access the same data. And then in 2000 we released a piece of software which is actually our first endeavours in Python. That's the Python logo back in the year 2000. So Python 1.5, as it was at the time, we produced a piece of software called Conquest, and that is still in use today. We have from time to time upgraded and imported it, so as of 2015 we ported it to Python 2.7. Might get ported to Python 3 at some point, but that's still in production, still used today, and it's kind of a testament to Python. I've got kind of a slide about that in a second. This is C++ visualization, OpenGL, very fancy tool. Obviously the web is the way forward. That's the PHP website there, which is fortunately retired. Through to today, where there's now a Python API to access this data, and everyone's much happier. So just going back to the Conquest program, I think, yeah, if you run this, load it up in PyCharm or something and look at the PEP8 analysis, it has a fit. It's not a surprise. And lots of developers will look at the code and they're horrified. But actually, when you put it into context, we wrote that code before the with statement was in Python. Generators didn't exist. The type and class models were different at that time. So the unified type and class model that we love nowadays wasn't actually introduced until 2001. But that's being an 18-year-old piece of software, which we don't have to treat as legacy software. It's kind of a testament to Python, really. It is understandable. Storing the data. So this is how we used to do it. At the start of the 70s, there was basically 3 plain text files, essentially. So one stores bibliographic data and some other textual chemical information. Then there's connectivity, so that's the chemical topology, so which atoms exist and how are they bonded to each other. And then data, so it's the 3-dimensional coordinates of each of these atoms. And they were linked with a unique identifier, which we called a ref code. That was a textual identifier that had some properties, which essentially means it's human pronounceable. And we still use those ref codes today. And that ref code basically tied together these 3 data files. There were binary versions of that for faster searching, but it wasn't until '86 where we formed a proper database as we'd understand a database, so I'm going to skip over that. So the ASA data format is our proprietary database format. It was developed from mid-80s to late 80s, really. And it was all in Fortran. And nowadays, if we looked at what it's doing, we'd scratch our heads in amazement. There's some huge limitations in it. But given the time, actually they're completely justifiable. So, for example, there was a 2 gigabyte file size limit, which we reached about 3 years ago. And so we've got a hack in place with multiple files to lots of 2 gigabyte sets. Size of the crystals was limited to 999 atoms, and to extend the data that's stored, so add another piece of data, it was a huge development effort. We released our software, the last release of our software 2 months ago, still had the ACER format in it. It's still used, so our desktop users, that's the main database they use. Come back to that though in a moment. This is what the architecture looked like though in 1989. So this is kind of the three-dimensional data, and some bibliographic data and chemical data, and these are basically stored in ACER file, so we're still calling it then rather than ACER database. Quest is the search engine. It's a piece of software, but also there's a Quest language. And you can think of that like SQL, but instead of tying into a relational database, it ties into chemical structures. All of that. I'll give you an idea of what we thought was a good user interface in 1989. So the equivalent would be is if you created a database management system, and the way you entered your queries would be to use SQL without abstracting away the SQL syntax or commands in any way. Your menus would be the SQL commands. That's pretty much what we did with the Quest language. Fortunately, our ideas of UIs have moved on. But justifiable question, why didn't we just use SQL? Well, this is why we didn't use SQL. SQL wasn't available commercially until 1979, and then it was still only available on VAX computers, by which point we were quite well established with our database. SQL wasn't an official standard until the mid-80s, and MySQL, which most people would probably be familiar with, wasn't released for the first version wasn't available until 95, at which point ACER had already existed for a decade. There's also the small matter that in the chemistry community it was believed that relational databases weren't the way to store chemical structures. That's not necessarily true today. Okay, so we have tinkered with SQL over the time. I'm not going to go into any detail here other than to say we have various variations on our ACER database in SQL. So actually calling this SQL is a bit of a stretch. It was a SQL database, but the data was still in binary blobs generally. The same Fortran binary blobs that is as well. We started unwinding them with binary blobs to XML, which made it a bit more extensible, a bit more useful to work with. Still not great, but this year, I don't want to jinx it, but our release in 2 months' time will not have the ACER format in it. We're moving to a fully relational database. I say fully relational, almost fully relational. It still has to have some blobs in it for performance-related reasons. But the nice thing about Python is you don't care about any of that format change behind the scenes. So our users now will have a completely different database. They won't care, they won't even notice. Okay, so I'll talk about that in a second, but the Python API. So in 2015 we produced a proper Python API. We had Python APIs before, but not covering our full kind of range of features. So if you care about some more details about this, you can follow the link, or just do a Google search for CSD. Actually, do one for CCDC and API, and you'll go to there. If you do CCD or CSD, you might find a different thing. But we introduced this into our desktop applications, it made them much more flexible, so thank you Python. But this is kind of the important part of the story. So those database changes, moving from ASA to SQL, hasn't changed the API from the user's perspective in any way. It's completely abstracted away. So here's a simple example. I'm afraid you might not be able to see that on the slide, the resolution isn't great. But this is my Python or Jupyter notebook. The first block there simply accesses one entry in the database. There's several ways to do it. You can do it through searching, but this is just, if you happen to know the index, you can pull it out. So it opens the data, which I'm saying is CSD, could be an in-house file or some other source of data. You request your entry, and that's it. And it's still the same, irrespective of whether you're doing SQL or ASA behind the scenes. And then just to flesh out the example, it just produces a 3D chemical diagram. So that's the sort of thing that back in 1970, someone would have drawn by hand and then used the puck to transcribe into the system. Nowadays, obviously, we auto-generate them with manual editors. Maybe minor tweaks where required for chemical reasons. Okay, and I had 3 or 4 slides trying to justify why the API was a good thing, and then on Friday, my colleagues were sharing a quote from a thesis that it's a draft copy of this thesis, not actually submitted. So this is a student at UCL. He's looking at crystal structure prediction, and he's using the CSD to drive that prediction. And his quote is, the release of the CSD Python API has brought an enormous advance as it allows access data more quickly and effectively, and to interface retrieved information with other tools to build workflows. And that sums it up perfectly. It's taken data which is in a proprietary database format, locked away. You had to use our tools to use it effectively. It's available openly through the API, and you can do what you like with it. So I deliberately chose an old photo here. I think this is from 2012 for the people who worked at CCDC. So I believe around 110 unique people have worked on the code base. That does include the technical documentation as well, actually. So plenty of people. And the result of their work is, and this is after spending a few months now deleting unused pieces of code, we're down to 2.1 million lines of C++, 280,000 lines of Python, though to be honest that does include quite a lot of auto-generated code, and unfortunately 480,000 lines of Fortran. But if I was here next year, I'd be able to say I'm predicting about 40,000 lines of Fortran. We're about to throw it all away in preference to MySQL. Thank you for your attention, and I'm happy to answer any questions. I actually had about double the number of slides before I ran through my talk for the first time. So if anyone's interested in this stuff, come and talk to me, and I can talk at you until you're not interested anymore.
I think we've got time for 2 quick questions.
Very quickly, from the 65 people currently working, how many of them are actual tech?
About a third of them are technical, so about 25 are directly related to software delivery products. There's 14 which call themselves C++ or Python developers, and I manage most of those people. So it's quite a big fraction.
So you said the database started out as some diagrams of chemicals and then some citations attached. So I'm wondering how the rest of the data got in, the data that can be queried, that chemists would want to query.
Yeah, so in the olden days, it's essentially the final data from the crystallography experiment was what was of interest. So the chemical topology, the structure, and then the coordinates, 3-dimensional coordinates of each of those atoms, which was basically in a paper somewhere in a big table of coordinates to 3 or 4 decimal places. one set of 3 numbers per atom. And then alongside that, there's some annotations to what the melting point of the crystal, because that came out of the experiment usually. Sometimes what the colour of the crystal was, what the shape of the crystal, so was it basically what it looked like. So if you look at table salt, it's kind of a cubic shape, for example. But actually nowadays there's very different sets of data. So lots more of the raw data is accessible. So we don't consider that part of the CSD, but it's stored alongside it, sort of the original readings. So actually, if I go way back to one of my early slides, I've got a picture. So this is showing electron density, which comes out of the experiments. So the data which encodes that electron density is available nowadays. This was from Dorothy Hodgkin. She basically got plastic layers and she drew by hand what the density would look like on that layer and contoured it up to produce that. Nowadays, obviously, we use computer systems. Does that answer your question?
I think we should call it time there. So thank you once again, Stewart.